Hello everyone, my name is Saadat and thank you for attending this presentation. We are going to talk about quantum computers. In particular, we are going to talk about a quantum circuit layout, which is basically an instruction on how to map a quantum circuit to a quantum computer. There is a strong motivation to know what is a quantum computer and how we can effectively use it. A classical machine will still be the easiest and most economical solution for tackling most problems. But quantum computers promise to power exciting advances in various fields, from material science to pharmaceutical research. Those fields usually require analysis of a big data or a very big data, and quantum computers promise us very attractive features. They have a potential to work at very high speeds in high parallelization, as well as to work on a level of quantum, which also means high compaction. Companies are already experimenting with quantum computers to develop things like lighter and more powerful batteries and new drugs. Overall, a quantum computer is an ideal tool to process big data, to accelerate everything you want. What is a quantum computer? Well, it looks like this. There are several models of quantum computing, including the quantum circuit model. It looks a lot like a classical computational model. As an input, we have classical bits, and as an output, we have measurements from the qubits, which may vary from experiment to experiment. Quantum circuits are based on the quantum bit, or qubit, which is somewhat analogous to the bit in classical computation. Qubits can be in 1 or 0 quantum state, or they can be in a superposition of the 1 and 0 states. However, when qubits are measured, the result of the measurement is always either a 0 or a 1. The probabilities of these two outcomes depend on the quantum state that the qubits were in immediately prior to the measurement. We send those qubits through a quantum logical circuit made from the quantum logic gates, which are somewhat analogous to classical logic gates. Those gates make some transformations to qubits. Therefore, a logical circuit consists of logical quantum gates, and we are designing an optimal algorithm of mapping those quantum gates onto a physical layout. There are a variety of quantum gates, but for now it is enough to know that there are 1 qubit and 2 qubit quantum gates, which perform quantum operations on 1 and 2 qubits respectively. There is a special gate called swap gate. It is denoted like a cross between two interacting qubits, and its function is basically to change their positions. For instance, here I have qubits A, B, C. If I insert two swap gates, one between A and B, while another one between B and C, then finally I have a configuration where the order of the qubits is B, C, A. We are interested in designing a circuit as cheap as possible. Therefore, we should establish the notion of the cost. The cost of a quantum circuit is a total number of 2 qubit quantum gates that are used to build the circuit. That's right, there might be several ways to design a quantum circuit layout, which will require a different amount of 2 qubit quantum gates. There may be different physical layouts, and we are looking for the best configuration for every of them. Also, we should note that the cost of a quantum layout is a number of swap gates used to map the circuit to a physical layout. Even though there exists a number of methods on how to build a layout, not many of them are looking at a quantum circuit in general. Existing methods focus on local optimization, which do not imply global minimization. In addition, because they are formulated on a bottom-up manner, the scalability is not guaranteed as well. Also, our goal was designing a mapping algorithm for circuits with a large number of qubits. I would like to show you how our algorithm works using the following circuit as an example. I would like to remind you, our goal is to determine a circuit layout to fit the logical circuit into the physical layout. Following our algorithm, for this purpose we should build a circuit interaction graph, CIG. The purpose of this graph is to show 2 qubit interactions. So the first step to make CIG is to create a circuit skeleton. A quantum circuit skeleton is a structure that remains after removing all single qubit gates and any logic on the interaction gates. The circuit skeleton, in turn, consists of generalized interaction gates, GI, basically every quantum gate acting on two qubits without logic applied on it. For example, in the circuit there is a C0 gate between qubits A and C, which will be represented as a GI between qubits A and C in a circuit skeleton. Now we can build a CIG. For this purpose, we map a circuit skeleton onto a graph such that every qubit will be represented by a vertex. GI is represented by an edge between two corresponding vertices. Each edge has a weight that is equal to the number of gates or interactions between its endpoints. Therefore, on CIG, edge AB has weight of 2, as there were two interactions between qubits A and B in the circuit skeleton. Likewise, edge BC has a weight of 4, because of 4 interactions between qubits B and C. Sometimes CIG doesn't have to be reduced in order to be mapped to a physical layout. We can say that CIG is isomorphic to some part of a physical layout, or is a subgraph of a physical layout. For instance, this graph can be directly mapped, but what to do with CIG like this? Let me remind you that the CIG represents the ideal or completely expanded geometrical model of a quantum circuit. However, as you can see, at this stage, the CIG may be oblivious to real hardware requirements. Meanwhile, a particular architecture allows for a limited and constant connectivity between qubits. So we need to reduce the graph, and we need the operation called an edge removal, ER. ER is a generic operation that can be performed on any edge. Thus, the ER operation can create several different graphs. ER causes the change of weights in another path between qubits A and B, because we must account for the swap gates which will be used to move qubits so they can interact. How edge removal affects the logical circuit? Well, here you can see the CIG and the circuit that it represents. If we remove the edge between qubits A and B, then there will not be any interaction between those qubits happening from their current positions on the logical circuit. Instead, we have to insert swap gates in order for qubits A and B to interact. There are two types of ER, consistent and inconsistent. The difference is that consistent ER leaves the graph connected, while inconsistent does not. Here, I made up some examples to show you how the proposed algorithm works. Even though they are a product of my imagination, there exist a number of real circuits that are either alike to this circuit or contain it as a subgraph. First step is to order the weights in a non-decreasing manner. Thus, we are making a priority list of edges. Then, break the edge with the least weight. If it doesn't result in an unconnected node, adjust all weights between the separated nodes by adding 2. Else, if it results in an unconnected node, as it is shown there, then we connect it back to a graph by minimizing the cost. This is done by ordering all nodes connected to the target node by distance from it in non-decreasing order and connecting it to the closest one. You may wonder, why did I just put back the edge connecting node Q3 to the graph? You see, if there is no other place to connect the node Q3, so the graph would be isomorphic to a physical layout, it is better to leave it as it was. Since connecting the node to any other place would increase the cost, as we would need to add swap gates for node Q1 and Q3 to interact. Thus, the total cost would change. But if we disconnect and then connect it back, then we are left with the same cost. And we repeat those steps over again until the desired geometry is achieved. Another question is, why do we order the edges in non-decreasing order? Why do we remove the weakest edge and why we don't remove the edge with the highest weight? Well, when removing a high weight edge, there is a large possibility that we have to insert a large number of swap gates. as we perform the naive insertion of swap gates, which means we move a qubit to some certain position and then we return it back to the original one. The smaller cost means less interactions, thus we end up inserting less swap gates. This is why it is important to consider CIG edge weights. When we remove the weakest edge, we obtain the smallest cost. Therefore, the ordering tells us the best edges to be cut. And this is how we obtain a mapping. Let me show you another example. It looks just like the previous graph, but the edge weights are a little bit different. Let's begin by removing the weakest edge with a weight 1. We see it again results in an unconnected node, so we connect it back by minimizing the cost. Next, we have to remove the edge with weight 5. Still, we see that this graph is not isomorphic to any part of a physical layout, so we remove another edge with weight 7. Now, it is indeed isomorphic to a part of a physical layout. To verify the proposed method, we use a Qiskit software development kit. The SDK provides access to physical quantum computers through an API called IBM Q Experience. Here, you can see example functions. For an explicit list of used functions, please refer to the paper. The CIG-based approach was evaluated using the IBM circuit compiler using various levels of optimization. In Qiskit, 3 levels of optimization are available, from the weakest to the strongest. The results of not optimized design is untitled cost, and the 3 levels of optimization using IBM native support are entitled cost I, where I is a level of optimization. Similarly, the CIG approach was applied directly or has been combined with IBM optimization of all 3 levels. We first applied our CIG-based optimization and then IBM optimization. The costs that you see are the costs of the total logic circuit with swap gates included that are used to map the circuit to a physical layout. We performed test runs on more than 170 benchmarks. In average, the CIG improvement over the best IBM result is 24.6%, with the lowest improvement being 26%, and the highest improvement was 64%. Our proposed method improved in some cases the default cost on the IBM Q approach. This is possibly due to the fact that our layout mapping uses guided global optimization and for a subset of circuits does a better job searching for the qubit placements, accompanying the randomized qubit placement algorithms used in Qiskit API compilers. Another fact worth mentioning that the improvement was achieved on the circuit that can be directly mapped to an IBM Q16 computer. So one of the areas for research of its possible applications is the use of the algorithm for optimizing circuits that can be directly mapped to IBM 16 Melbourne. In the future, we plan to provide a full set of functions integrated into a library that can be integrated in other algorithms, solving the quantum layout problem. Our implementation could alternatively find its place as one of the optimization layers for quantum object compilation. The next step in the final development are going to be including the direction of coupling-sensitive synthesis, noise-related optimization, SAT solver for the optimal mapping, and adding local minimizations, as well as optimizing the swap gate insertion and edge removal. Once all these features are implemented, a testing and comparative analysis with other state-of-the-art algorithms is to be performed. Thank you! This is all for the presentation, and now it's time for a Q&A session.